All right, let's dive right in. Today, we're going to think small. I mean, really, really small. We're exploring the world of materials built with atomic precision, a technology that is fundamentally changing how we create, well, everything, from the computer chips in your pocket to the next generation of electronics. So just imagine for a second. What if we could actually build our world not with bricks and mortar, but by placing individual atoms exactly where we want them? I know. It sounds like something straight out of science fiction, right? But the thing is, it's fast becoming our reality in a field that's just shattering the boundaries of what we thought was possible. Okay, so to understand how we do this, our journey has to start in a place that scientists kind of poetically call flatland. We're talking about a world where materials are reduced to their absolute thinnest possible form, just a single layer of atoms. And these are what we call 2D materials. You know, try to picture a sheet of paper that's so unbelievably thin it has, well, no thickness. That's the core idea. But here's the crazy part. Unlike paper, these atom-thin sheets have properties that are almost magical. I mean, you're talking stronger than steel, more conductive than copper, and some are perfect insulators. It's that wild mix of properties in one place that makes them such a huge deal. All right, so you've almost certainly heard of the superstar of this world, graphene. But, and this is super important, not all graphene is created equal. This table right here breaks it all down for us. You've got true graphene, right? That's the perfect single crystal sheet of carbon. It's unbelievably strong and conductive. But then you look at graphene oxide, or GO, and it's loaded up with oxygen, which actually makes it an insulator. And then there's reduced graphene oxide, RGO, which kind of lands somewhere in the middle. Trust me, these differences mean everything when you're actually trying to build something. And hey, it's not just a one-trick pony with graphene. Let me introduce you to its cousin, hexagonal boron nitride, or HBN. People call it white graphite because it has that same layered thing going on, but its properties completely opposite. It is one of the best electrical insulators we know of, even when it's scorching hot, like 1,000 degrees Celsius. But at the same time, it's an incredible conductor of heat. So you get this bizarre, amazing combination of being a super insulator that's also super slippery. It's just a wonder material. So the big question is, how on earth do you make these things with such insane precision? Well, let's look at the first method, which is, honestly, it's like construction, but on an atomic scale. It's a technique called Atomic Layer Deposition, or ALD for short. And really, the best way to wrap your head around it is to think of it as the ultimate form of 3D printing, except instead of squeezing out plastic, you're laying down a perfect single layer of atoms, every single path. Okay, so it works through this super precise 4-step cycle. It's like a recipe. First, you pulse in chemical A, and it just sticks to the surface. Step 2, you flush everything out with an inert gas to get rid of any extra A that's just floating around. Then, step 3, you pulse in chemical B. Now here's the key. It only reacts with the A molecules that are already stuck on the surface. And finally, step 4, you purge again, and what's left behind? Exactly one flawless atomic layer of the material you want. And right here, you can really see that perfect cycle in action. Look at that. The first chemical comes in, coats the surface. Then the second one comes in and reacts, and boom. Just like that, you've grown the film by precisely one atomic layer. You just keep repeating that recipe. Pulse, purge, over and over, until the material is exactly the thickness you need. It's incredible. And this right here, this is the real magic of ALD. The secret sauce, if you will. The process is self-limiting. What that means is, because the second chemical only reacts with the first one, the reaction literally stops itself once one full layer is complete. You can't mess it up. You can't add too much. It's a built-in guarantee for perfection and uniformity, every single time. It's almost foolproof. And of course, the tech doesn't stand still. So you have your traditional thermal ALD, which, as the name suggests, uses heat to get the reaction going. That's great for a lot of oxides. But then there's plasma-enhanced ALD, or PALD. Now this is cool. It uses a super high-energy gas, a plasma, to kickstart the reaction. And what does that let you do? Well, for one, you can work at much lower temperatures, which is absolutely critical for delicate electronics. And two, it opens the door to creating a whole new range of materials, like pure metals, that are really tough or even impossible to make with just heat. Okay, so if ALD is all about building up, this next technique is the complete opposite. It's about carefully peeling things apart. So another way to do this, instead of building up, atom by atom, we can take a layered material and just gently pry it open, like a book, one single page at a time. And this image here just illustrates that whole journey perfectly. You start with this solid chunk of material, right? Then you kind of swell it, pushing the layers apart with other molecules. And then you gently separate it all in a liquid. And what you end up with is a solution full of these individual floating nanosheets. It's a really elegant way to go from a big 3D chunk to a pristine 2D material. So how does it work? Well, it's basically a 3-step process. First step is intercalation. This is where we slide other molecules or ions in between the layers. Think of them like thousands of tiny bookmarks to start pushing them apart. Next is exfoliation. Here we use some gentle energy, maybe just shaking it or using sound waves in a liquid, to break those now weakened layers apart into individual sheets. And finally, purification. We spin the whole mixture in a centrifuge, which neatly separates the perfect single layers from any unexfoliated chunks or leftover chemicals. Okay, so we've got these incredible techniques for building things atom by atom, building up, peeling apart. But this isn't just some cool science experiment for a lab. The really big question is, so what? Why does any of this matter? How is this stuff actually going to show up in our lives? Let's start with just a number. 1.43. 1.43. What on earth could that be? It seems totally random, right? But I promise you, this number is a massive deal in the world of electronics. So 1.43 is what's called the K value, or dielectric constant of an amorphous boron nitride film, one made with that plasma technique, PEALD, we just talked about. In simple terms, the K value just tells you how good a material is at being an insulator. A perfect vacuum is the ultimate insulator, and its K value is 1. So getting a solid material with a value this low, this close to 1, is an absolute game changer. It's what you need to stop all the tiny wires inside a computer chip from talking to each other and messing things up. And here you can see what that actually looks like. This image shows that super precise ALD process being used to deposit that insulating layer. You can see it as the bright areas, only exactly where it's needed on a microcircuit. I mean, look at that precision. This is the kind of control that lets us keep making our computer chips smaller, faster, and way more energy efficient. And look, when you're building with individual atoms, you better have a way to check your work, right? And that's where these amazing tools come in. On the left, you've got something called Raman spectroscopy. Think of it like a high-tech scanner that confirms the chemical fingerprint of your material. Did we make what we thought we made? And on the right, that's an image from an atomic force microscope. It's basically like feeling the surface with a needle that's only 1 atom wide. And what does it show us? A flawless, ultra-smooth surface. It's the proof. It shows we can not only build at this incredible scale, but we can see and verify our work with that same mind-blowing precision. So at the end of the day, whether we're building materials up atom by atom or peeling them apart layer by layer, what we're really doing is we're learning to speak the language of atoms. And that, of course, leaves us with the most exciting question of all. Now that we're starting to get fluent, what are we going to ask them to build for us next?